Today we are looking at chapter 13, physics chapter 13, and the topic of today's class is electromagnetic spectrum. Electromagnetic spectrum. Okay, without much ado, let's begin quickly. This is an aspect of our daily life that we come in contact with or encounter with without us realizing. First of all, you remember in chapter 12 we studied the light, right? And then we said light is a form of, the sunlight is a form of a visible light. However, visible light is not the only electromagnetic radiation or electromagnetic wave that is emitted by the sun. About 7 to 8 of them are emitted by the sun, but the one that our eyes can see is called the visible light. The part of the electromagnetic wave that our eyes can see is called the visible light. But we're going to look at all the other aspects of the electromagnetic wave that we cannot see with our bare eyes, with our naked eyes. So, however, you remember in chapter 12 we said that the sunlight produces a spectrum of colors whenever we pass it through a triangular prism. When we take the sunlight and pass it through a triangular prism, it produces about 7 different colors. And we're going to look at this color. We're going to look at the triangular prism. And this process is called dispersion. So you need to take note, especially in multiple choice questions in Cambridge IGCSE exams, because when they ask you whenever a narrow beam of white light is passed through or is refracted through a triangular prism, several different rainbow colors are produced. And these several different rainbow colors, the process itself is called dispersion. Okay, the process is called dispersion. Let's write the word dispersion, because you need to know this word, you need to know the definition, you need to know what it means. Dispersion. Dispersion is the process whereby a narrow beam of white light refracted through a triangular prism produces several different rainbow colors. Produces several different colors. We're going to itemize this color and we're going to show them and their wavelength, or which of them has the longest wavelength and which of this color has the shortest wavelength. As red is seen to be the one with the longest wavelength, and violet is seen to be the shortest wavelength. Now let's take a look at, so we should be able to define dispersion. Dispersion is the process whereby a narrow beam of white light or sunlight, whatever you want to use, whatever terminology you want to use, whenever a narrow beam of light, you know what that means? It means many rays of light. Okay, beam of light means many rays of light put together and is made narrow. A narrow beam of white light is shown through a triangular prism. Remember, it's a triangular prism. This experiment was done by the scientists in the late 1880s. Okay, so whenever a narrow beam of white light is shown through a triangular prism, this is a 3D shape. Remember, it's not just a triangle. A triangular prism, then it will refract to produce several colors. The refraction starts within the glass prism, and then outside here they'll be refracted again to produce several colors. These colors are Roygbiff. The mnemonics for remembering this color is called Roygbiff. Okay, the first one is the red one, then the orange one, then the yellow one, and then the green one, then the blue one, and then the indigo, and then you have the violet. So you have several different colors, rainbow colors, that will be produced, and this process is known as dispersion. So we should be able to explain when one of the visible light itself, the one we can see. We're going to talk about all the electromagnetic wave. Remember, the visible light is just one of the electromagnetic wave. Visible light is just one of the electromagnetic wave. There are about 6 or 7 of them, or 8 of them we're going to look at. But visible light is just one of them. That this visible light, which is the sunlight, which can be seen by our eyes, whenever it's shone through a triangular prism, it's going to refract. You remember we studied in the past chapter, we studied refraction. Okay, it's going to refract, meaning it will bend when it enters, when it changes medium. Here is air. When it enters this triangular prism, it becomes another glass. Glass prism becomes another medium. So it's going to refract. The ray will refract and produce several colors. And when they get to this other boundary, then it will refract more, and more of it will be ousted. So this process is called dispersion. And the light that is produced by the visible light is called spectrum of light. These several lights that is produced, or several colors of light that is produced by this process is called the spectrum of light. So we should be able to tell or explain all these things in the proper perspective. What are the main regions of electromagnetic spectrum? The main regions. So we're going to look at all the spectrum of or all the waves of the electromagnetic light. Light from the sun travels as electromagnetic wave, right? Now these waves are different types and they make up the electromagnetic spectrum. But remember, our eyes can only see only the visible part of it, the visible light, the one we call the visible light in the spectrum. Other waves that are found or that are present include the radio waves, include the microwaves, include the infrared. Remember, the visible light is the only one we can see. Okay, this is the spectrum which we're going to explain right now. So we have the visible light, and then we have ultraviolet, we have X-ray, and we have a gamma ray. All of these EM wave, they are called EM wave, electromagnetic wave. EM means electromagnetic. Electromagnetic. So we call it, for short, we call it EM waves. Okay, we call it EM waves. So whenever light is being emitted by the sun, it has all these electromagnetic waves. All these are the waves or lights that are emitted by the sun. However, our eyes can only see this one, this visible light. Our eyes can only see this. So this is called the spectrum of electromagnetic wave. The spectrum of electromagnetic wave. This visible light is one that produces seven rainbow color. Only this one alone is one that produces the seven rainbow color, the royal beam I've talked about just now. So this one is one that produces those seven colors, the red, the orange, the yellow, the green, the blue, the indigo, and the violet. All of those seven lights or seven colors of lights are within the visible light in the spectrum of electromagnetic wave. Now let's take a look at the first one, which is the radio wave. Let's say we draw a spectrum. We give each one a triangular box, a rectangular box, sorry, a rectangular box. You have the radio waves here. You have the radio waves. You have the microwaves. You have the infrared. You have the visible light, right? We have the ultraviolet ray. We have the X-ray. We have the gamma ray, right? 1, 2, 3, 4, 5, 6, 7. Seven of them. Okay, the seven electromagnetic spectrum. Now, if you look at this one, this is called frequency. Okay, you know, what do we mean by frequency? Within a second, how many of this complete wave is formed? If you look at it at the beginning, it's not very frequent. Like the frequency is very low. As you go to the right, to the gamma ray, as you move from the radio wave to the gamma ray, you can see it's more frequency. Meaning, if you are going from the radio wave to gamma ray, the frequency is increasing. It starts from 10 to the power of 4 for radio, 10 to the power of 4 for radio waves, and the radio wave ends as almost 10 to the power of 9 or 10 to the power of 8. So for radio waves, so from 10 to the power of 4, which is 10,000, to 10 to the power of 9, which is almost 1 billion. This is the frequency of a radio wave. Within this spectrum is the frequency of a radio wave. Now from 1 billion to about, let's say, 1 trillion is the frequency of a microwave, is the frequency of microwave, right? Then after microwave, we have infrared radiation. We call it infrared radiation. We use it for so many. We're going to discuss the uses of each of these, how the application of each of these, even though we cannot see them. Remember, we cannot see a radio wave. We can see the microwave. We can see, it's not the microwave oven, but the microwave oven has the quality and it possesses the characteristics of microwaves radiation. Now we have the infrared, okay, the one that is being used by remote control, infrared radiation to control our television. Those are infrared radiation. Okay, then there are several colors of light, which are the Roy-Beef, is the visible light. Okay, the one that is shown on a triangular prism to refract and produce a spectrum of light. And then we have ultraviolet ray, which is from 10 to the power of 14 to 10 to the power of like almost 15 or 16. Then we have the X-ray, which is 10 to the power of 16 to 10 to the power of 18. And then we have the gamma ray, 10 to the power of 18 to 10 to the power of 20 or 21. Okay, so that's the frequency of this. So if you're going from radio wave to, you need to know this. You need to like have an idea of the band of frequency for each of them, and from where to where is the frequency increasing. So when you're moving from radio wave to the gamma ray, the frequency is increasing. That's called increasing frequency. Remember, the unit of frequency is Hertz, Hz. Okay, increasing frequency. When you're going from radio waves to gamma ray. Now, on the other hand, the wavelength decreases when you are going from radio wave to gamma ray, or you can say it alternatively, the wavelength is increasing when you now move it backward from gamma ray back to radio wave. The wavelength increases, meaning the radio waves have a bigger wavelength compared to the gamma ray. The radio waves has a bigger wavelength. So wavelength is like, in this case, is like opposite of the frequency, opposite. So as you go from radio wave to gamma ray, the frequency decreases. If you are going from left to right, from radio wave to gamma ray, the wavelength decreases. However, you can put in a proper perspective by saying, okay, now we are going from the gamma ray to the radio wave. When you're going from gamma ray to radio wave, the wavelength increases. Wavelength is in meter. The unit is in meter. The gamma ray wavelength span from 10 to the power of negative 12. You can see how that's small. So it means 0.000000000000001, something like that. 10 to the power of negative, you can see how small is the wavelength of a gamma ray. 10 to the power of negative 12 to 10 to the power of negative 10. That's the wavelength band of a gamma ray. Therefore, X-ray is 10 to the power of negative 10 to 10 to the power of negative 8. That's the wavelength band of a gamma ray, of X-ray. Then the ultraviolet is 10 to the power of negative 8 to 10 to the power of negative 6. You find the ultraviolet radiation. Then the visible light is around 10 to the power of negative 6. The visible light itself is within the arches of 10 to the power of negative 6. Then from 10 to the power of negative 6 to 10 to the power of negative 4, you have the infrared radiation for the wavelength. We're describing the wavelength now. Then from 10 to the power of negative 4 to 10 to the power of negative 1, which is 0.1, right? Yes, 0.1. 10 to the power of negative 4 to 10 to the power of negative 1, you have the wavelength of the microwave. You have the wavelength of the microwave. Then from 10 to the power of negative 1 to 10 to the power of 4. 10 to the power of 4, you have the wavelength, meaning 10,000. So you can see the radio will have a very big wavelength. You have the wavelength, ranges for the wavelength of the radio waves. So we need to know how to draw the spectrum. In the exam, we need to show the increasing frequency from this side to this side and increasing wavelength from the opposite side, the gamma ray, to the radio waves. Okay, so this is what we call the EM spectrum, electromagnetic wave spectrum, electromagnetic wave spectrum. Remember, we have discussed the electromagnetic wave. We say it has different ranges of wavelength and frequency. For example, the visible light ranges from violet with the shortest wavelength and red with the longest wavelength. Like these are the visible light has several rainbow color. When you shine it through a triangular prism, it first emits red color, which has the longest wavelength. You have orange, O is for orange. This is a mnemonics, a short form of remembering the rainbow color, which is the spectrum of visible light. The first one is the red one with the longest wavelength. You have the orange color next to it. You have the yellow color. You have the green color. You have the blue color. You have the indigo, and you have the violet. Violet has the shortest wavelength. Remember that. Violet, which is the last one, has the shortest wavelength. It has the shortest wavelength. Okay, now that's for that. Let's move on quickly. EM waves travel at high speed in a vacuum. We know that, right? Electromagnetic waves travel at very high speed. We know the speed of light, right? We already know the speed of light. In many cases, we use the speed of light, which is 3 times 10 to the power of 8 meters per second. In 1 second, it will move 300 million. Okay, 300. This one is 300 million meters per second. In a second, a blink, 300 million meters in 1 second. That's the speed at which any of the EM wave travels in space or in vacuum. Okay. Now remember, in chapter 12, chapter 11 and chapter 12, we studied the formula for the speed. We said the speed is given by the wavelength. Remember, this is the symbol for wavelength. It's actually a lambda, a Greek word, lambda, which represents the symbol for wavelength. It's the wavelength times frequency. Okay, is it that we use this? Or in the case of time period, we say the speed is the wavelength is equal to the wavelength over the time period. Equal to the wavelength over time period. You must be very good in recording physics formulas and their units, okay? So is it that we say we use this formula for calculating the speed, or we use this one, the speed equals to lambda, which is frequency, which is wavelength times multiplied by frequency. So if you're looking for wavelength, you just make wavelength the subject of formula. You just make wavelength the subject of formula. Okay, so wavelength will be the speed divided by the frequency. Wavelength will be speed of the electromagnetic spectrum over the frequency. This will be the wavelength formula. Okay, so this is the formula for wavelength and formula for speed in any of this electromagnetic wave. Okay, here are some questions. You pause the video, try to answer these questions, okay, before you continue. Now let's move on to what are some of the uses of electromagnetic radiation. What do we use each of this one for? Okay, what do we use each of these for? Okay, we start with the first one. I think the first one is radio wave, right? Okay, the radio wave. This is one that is used in telecommunication for transmission of radio and television signal. Okay, you see all this. Just take what is very important, and then we move on. We say the microwave, which is the second one, right, in the EM spectrum, electromagnetic wave spectrum. Okay, the first one, remember, is the radio wave. Okay, I think we should discuss them according to the way they come in the spectrum. So let's start with the radio wave before we go to. Let's start the discussion from the radio wave. Okay. Now, what are radio waves? We say they are the lowest. They have the lowest frequency and lowest energies. If you look at the spectrum, the radio will have lowest frequency. You know, the frequency increases as you go from radio waves to gamma rays. The frequency increases as you go from radio waves to gamma rays. So these ones, they have the lowest. They have the lowest frequency, and they have the lowest energy. They have the lowest frequency and they have the lowest energy. That's radio wave for you, okay? That's number one. So what do we use that for? I already mentioned, I said they are used in telecommunication, right? They are used in telecommunication for transmitting radio and television signals. They are used in radio and television transmission, right? To broadcast. They are used in the tall broadcast tower to send radio waves out into the air and to receive them on the other side of the divide, okay, to receive these waves on the other side of the divide. So this is what we need to know with regards to this. They are used for transmitting television signal, radio signal, FM and AM. You remember we used to have FM radios and AM radio, amplitude, frequency modulated radios and amplitude modulated. You're going to learn that one in higher level, A levels and in your degree programs. Okay, AM radio, that's amplitude modulated radios and frequency modulated FM, frequency modulated radios. Okay, so these signals that are being carried by radios they are called radio waves, and the ones carried by your televisions. Okay, when I'm saying television, I'm not talking about the satellite television. I'm talking about the normal TV program, TV. Depending on where you. We are not talking about satellite television. You know, satellite television like Astro TV, they are satellite television. Like the TV, TIGA, TV1, TV2, TV3. All those ones are the waves, the signals are carried by radio waves. They are called radio waves. The signal carried by those things are called radio waves. We go to the second one, which is the microwaves. Now, microwaves, they have the wavelength. They have wavelengths that are longer than the infrared. Okay? Their wavelength is longer than that of infrared. Let's see which position they are. Microwave, their wavelength is increasing when you're going. Microwave, their wavelength is what? Their wavelength is longer than that of infrared, but smaller than that of the radio wave. So that's what it is. Now let's move on quickly to it. So we say microwaves, they have wavelengths that are longer than that of infrared. They cause water molecules in food to vibrate and heat up very quickly, right? Okay, they cause it to, the effect is used in microwave oven for cooking. So they generate radiations that can easily and quickly cook our food. They can easily and quickly cook our food. Okay, some of the microwaves can penetrate clouds. They can penetrate artificial satellite. They can penetrate artificial satellite and so on and so forth, right? So microwaves are used in satellite televisions also. They are used in satellite phones and satellite television to transmit and broadcast satellite signal. They are used in geostationary satellite to beam the broadcast, or to beam broadcast television, or to beam the television signal directly to homes. Okay? To beam the television signal directly to our homes. So they are using geostationary satellite. You know, geostationary satellites are not too far-fetched from the Earth atmosphere. So they help to carry signals from one part of the world to another part of the world. They are also used in satellite phones. You know, we have mobile phones that we call satellite phones. So the microwaves are used in satellite phones. They are used in microwave oven for cooking food. They are used for satellite television broadcasts and so on and so forth. They carry satellite signals. Is that okay? So that's our second one. We go to the third one, which is infrared light or infrared radiation. Now, infrared has wavelength longer than the red light. They have the wavelength longer than red light. You know, red light has the longest wavelength, right, in the visible light. You know, wavelength has the longest light in the visible light. Look at the visible light. The visible light is just only this spectrum, this place. Okay? It contains about 7 spectrums of light, the Roy beef. They are all here. The first one is red, second one is orange, third one is yellow. They are all here, all the visible light. So we say the infrared has a wavelength longer than that of the first one here, which is the first one here has 10 to the power of negative 6, which is 0.0000001 meter. Okay, so that's for the red light, the red color of the visible light. So the infrared, the wavelength goes to 10 to the power of negative 4. Remember, negative 4 is bigger than negative 6. Negative number, the smaller the bigger. The first one, which is 10 to the power of negative 6 of it, the wavelength is even bigger. The wavelength of infrared is bigger than that of the red of the visible light. Okay, now let's move on quickly. So we know what it is. Now we say it causes heat and is used to generate heat. So people use the infrared lamps for warmth. They use it to warm their environment, and also they sometimes use it for pain relief. And we use it in remote control. Okay, the light you shine, the red light from here, from the remote control that you shine to your TV to control your TV is called the infrared light. It's called the infrared light. Okay. Okay, we say it's used in remote control and other LED compartment, LED communication devices. Okay, infrared transmitters. We have infrared transmitter detectors. They're used to detect intruders. We use infrared transmitter to detect intruder, to jam signals in other or block signals in other evading equipment. Okay, especially in warfare, we use infrared to detect maybe missiles and other things that can intercept and so on and so forth. Another thing we forgot to mention in radio wave, we have what we call radio frequency identification. Radio frequency identification. This RFID, when you are driving to a place, you don't even need to touch. The place will open for you. This is part of the radio waves, okay? So radio waves is used for RFID identification or readers, RFID readers and RFID trackers, okay? Okay, I think we didn't finish. Let's take a look at the others. We didn't finish the uses of all of them, but we have to go on quickly because their uses are kind of similar right now. We have what we call, after the infrared, we have the visible light, which we already know what we use it for. The visible light is the one that has the 7 colors. Okay, that is shown through a triangular high definition television. Can be used to scan or to detect what is inside our body. We can use the X-ray for medical uses to check what has happened to our bones, our flesh, what if anything has happened to us. So X-ray can be used to scan our bones and our muscles to see if there is any fraction or any spray or any broken aspect of our body. Then the gamma rays. The gamma rays, as we know it, can be used for curing cancer. The gamma ray radiations can be used to cure cancer, can be used for sterilizing medical equipment. Okay, can be used for sterilizing medical equipment and so many other uses. Can be used also. It has also a harmful side, which is itself can cause cancer, and it can be used as stem cells for the cure of cancer. So if you're going to be a medical researcher, yeah, I think we go some of the harmful effect of electromagnetic wave. So not all the good news that it has. It also has some harmful side. Also has some dangerous side. Now let's take a look at them one after the other. We start with the infrared radiation. Excessive exposure to infrared radiation can cause the skin burn. When you are too exposed, that's why don't be too exposed to the sun or any infrared radiation environment. So it can can burn your skin, it can cause skin burn. That's one big negative effect. Now, what about microwave? Excessive exposure to microwave can cause internal heating of body cells. Our body cells will start to heat internally, which is very dangerous, okay? Which is dangerous to our health, which can lead to these other diseases like cancer and other diseases in the body. Now, what about ultraviolet radiation? It is invisible, right? You know you don't see ultraviolet with your eyes. Invisible part of the sunlight. It's part of the sunlight that you don't see that can cause damage to the surface cells in our skin and our eyes. So don't use your eyes to be looking at the sun too much. It can damage the cells of your eyes. Excessive exposure to ultraviolet radiation can cause skin cancer. So be careful the way you expose yourself to ultraviolet radiation. It can cause skin cancer. What of X-ray? What are the negative effects from X-ray? They can damage the body cells. Yeah, that's why it's not good every little thing you go and take X-ray. Any small thing you say, oh, chest is paining me, I have to take X-ray. It's not good. In fact, medically, you cannot, once in every 6 months, the minimum time you can use, once you use it now, in the next 6 months, you cannot take another X-ray. Because too much, excess of it can damage the body cells. And excessive exposure to X-ray can cause cancer as well. Can cause what? Cancer. Our plants, they wear a protective garment of the entire body cells, okay? So these are some of the harmful part of it. Now let's go to the third one. You pause the video and answer the following questions. Okay, these questions are meant for you to see whether you follow. Okay, pause the video and answer these questions and see if you flow through it. Now let's go to a calculation, at least to see whether we understand what we're talking about. It says, how long does it take a microwave signal to travel from Earth to a geostationary satellite of 36,000 kilometers away and back? How long to go and back? Okay, you can see 36,000 kilometers is to go, and plus another 36,000 kilometers to return. So total will be 72,000 kilometers. So if you put a meter, you know you have to add 3 more zeros, which will be 72 million. If you add 3 more zeros, which is 72 times 10 to the power of 6. If you put in proper standard form, it will be 7.2 times 10 to the power of 7. Okay? Now remember the speed of microwave is 3 times 10 to the power of 8 meters per second. Now you have the distance. You have distance, you have speed. So time is what? Time is what? Distance over speed. Remember the time formula, right? Speed is distance. Speed is v. Speed is distance over time. So if you make time the subject of formula, time will be distance over speed. Speed is distance over time. Now if you make time the subject of formula, time will be distance over speed. Remember this is the distance. Okay, so this distance divided by the speed, we get the time it took. It took only 0.24 seconds for this Yungu to travel to the satellite and return back. Is that okay? Now let's move on. That's one question, one calculation question. Now we go to the next phase of this chapter, which is called signals, communication signals. Okay, we go to the next phase, which is called the communication signals. So we have two types of signal. We have the analog signal and digital signal. We have the analog signal and we have the digital signal. Communication signals. So we have two types of signal. We have the analog. What's the meaning of analog? An analog signal has a continuous value in time. Means a continuous wave. If I draw a graph, y-axis and x-axis, when a signal is continuously wavy like this signal. Okay, these are continuous wave. Or these are continuous wave. So whenever a signal is a continuous wave in time, that means the value continuous wave in time is called an analog signal. We're going to look at the step-by-step definition. But what is a digital signal? A digital signal has fixed value. It has like binary of 1 and zeros, or what we call on and off. On, off, on is 1, off is 0. Okay, a digital signal has only two digits, 1 and 0. Look at the digital signal. Okay, when you're on the 0 is the x-axis, which is the time axis. Okay, and the 1 is the maximum peak. So you can see a digital signal goes like this. Okay, this is the pulse. Pulse. This is a digital signal. Here now is zero. Is zero, maybe 2 zeros. You can see the width of this one is twice the width of this one, right? So here is like 1, 0, 0, and then you go again. This is 3 of it. 1, 2, 3, or 4. 4. I think this will be 4. 4 ones. 1, 1, 1, 1. And then you come again, you have 1, 0. You have 0 here. And then, see, it's binary. Ones are 0. You have 1. You come down. This is a digital signal. Then you have 0. You go again, you have 1, 1, and then that's it. So digital signal is about ones and 0. A digital signal is a discrete value of ones and 0. A digital signal is a signal with a discrete values of ones and 0. A digital signal, so every of our voice will be converted to digital signal before it can be transmitted. Okay? We have what we call ADC, analog to digital converter. You're going to study that at higher level. So a digital signal will be a signal like our sound is an analog signal. Hear it in our phone. Okay? And we absolutely thank you